Good morning everyone. We have come to the tutorial session of our course, and I have prepared a tutorial and asked it to be emailed to all the participants, and hope that you have received. If you have not received, please contact the course coordinator. They will send the two documents to you. They are two PDF files. First one is what you can see in the screen, mini hydro power plant design and integration with DC microgrid, tutorial 1, and our day, and it has 2 pages, and then there is another page containing a map, a portion of a map. And so, these are the 2 documents that must have been emailed to you. So, please download them, and I want you to work on it. So, the tutorial says figure T1 shows a contour map to scale of 1 to 50,000 for a hydropower potential area. Contour heights are given in meters. Suppose no other hydropower schemes have been implemented this area, and you are entrusted to develop a suitable hydropower scheme with a head between 100 meter to 250 meter in any river section shown in the map. Mark the location of the weir, that is diversion point, canal path, forebay tank, penstock and the powerhouse for the selected project on the map. Estimate the gross head of the project, that is the part A. Right. So, I want you to, on the this figure, using this drawing tool, you can freehand draw, mark these points in the map, right, right, and you must not select, I will just enlarge it a little, and you can refer to the video where we discuss contour maps. If you cannot remember, please refer to the video where we, I hope that it is accessible to them, video is accessible to them. So, refer to that section where we discuss about contour maps and this section, and then you try to do it, and in selecting, now this is a good river, right, this is a good river, but do not select this hairline like small rivers, streams, they are very small, their catchment area will be very small. So, do not select such rivers for your project. Right. Select something like this main river, and where you have opportunity for potential power projects. Right. So, and then it says further in section B, of the tutorial, it says the table overleaf shows the average flow regime in cubic meters per second for a small hydropower project in the area shown in contour map in figure T1. So, that is the page 2. Here you can see daily average flows that we discussed, which have been prepared by a hydrologist, right. So, October 1st flow is this much, and so on, right. So, it is given for all 365 days, and then further the tutorial says section B 1, assuming the given flow data table is applicable to the diversion point of your plant. Now, you have marked a diversion weir in your section A. So, assuming that this table is applicable to the river flows that are coming into this point, right, this at the diversion point is applicable to the diversion point of your plant selected in section A above. Prepare the flow duration curve for the location. So, you can again refer to the video where we discussed how the flow duration curve to be prepared. Select flow corresponding to 12% exceedance. Exceedance means the horizontal axis 12% in the flow duration curve as the rated flow. Determine the type of turbine and its capacity. I think you remember that we referred to turbine selection chart. So, you can refer to a turbine selection chart. If the video is not clear, you can search in the internet, small hydro or mini hydro turbine selection charts. So, similar charts will come up then in the images gallery. So, you can refer to one of them and select a suitable type of turbine for your head and your flow rate, your rated flow rate, which you derive from the flow duration curve you have created. Determine the type of turbine and its capacity. Assume single turbine power plant. So, we assume we are going to have one single turbine. Estimate the annual electricity generation in kilowatt hours or megawatt hours or gigawatt hours. That part we discussed in another discussion. So, you can refer to that section of the video and do it. So, I plan to allow you the first hour, that is 9:30 to 10:30, in fact until about 11 o'clock. So, I will start the next explain the tutorial at 11 o'clock, right, and help you. If you wish, you can even share, I hope that it is possible, you can even share your screen and ask me any questions. So, show me your workout if you wish, right. You can share your map where you have marked the things, and if you have doubts and any clearance, you can ask after sharing. But I will not be able to do with everybody, but maybe with at least few people I can do it, and then if necessary I will work out it. I will work out the flow duration curve part and the energy generation part depending upon our time availability, and help you, because finally you should be able to do these things yourself, otherwise just watching the video and doing it will not do, right. So, try to do it yourself and have your questions and queries lined up, and during the discussion session which we will start at 11 o'clock, we can go ahead with the further discussion. For the time being, if you have any questions now, you can ask. If you have not received your documents, you can also tell. Otherwise, I will stop here and allow you time to do the tutorial yourself, and then come at 11 o'clock to discuss it and further clarify. Any questions you can raise? Hope everybody you have received the documents. Yes, sir, we have shared the document. Okay, good. So, they have shared the document. So, please download into your computer and follow the instructions given in the tutorial page, and then look at the data table, that is flow data table given on the overleaf, and look at the map, and then try to do it yourself. That is the final intention of participating in this course. You should be able to do these things yourself. So, the first part of the question is to mark the location of weir, canal path, forebay tank, penstock and the powerhouse for the selected project on the map. So, here is the map. I will make it a little larger. Okay. So, obviously, there are many opportunities here, large project opportunities also. So, we will go for this main river here. Here is the main river, here, and there are, you can see various contour heights are marked. So, there are many opportunities, but we can use any of them. So, we can see that there are many contours we can use, but here it is up to the choice is up to the selector who is going to design it. So, I will so we are asked to have about 100 to 200 kind of head. So, we can see between any of these brown dark lines, it is 100 meters head difference. So, we can select accordingly and select a suitable place. So, and also there are choices that you can go in the right bank or in the left bank. So, how do you say left bank and right bank? When you stand somewhere and look at the flowing water, that is downstream, then your right bank is this one, left bank, that is the convention, left bank is the other one. So, this is the left bank, therefore, this is the right bank, right. So, we can go either way, but the choice is we normally look at obstacles, if there are people settled and houses built or any agricultural projects. So, we will try to avoid interference as much as possible, and then decide whether to go on the left bank or the right bank, right. So, let us see that so we decided to divert water here at this point, that will be the diversion weir. Right, and then you can go on this contour line. that will be your canal path and come to a suitable close location to the river. Let us say we came here. There are other options also, and then decide to have the penstock here, right, penstock here, and the powerhouse somewhere here. Okay, the operator is asking for some time, let us see. Okay. So, so we can now change the colors. You can see we came along this line, and here we have the forebay tank. I write FB as forebay tank, and then the penstock here. This will be our penstock. Again, I can't write. Okay, anyway, you can see, right, penstock here and the powerhouse here. So, that is a typical project. So, then we can count the number of contours we are cutting, right. So, here we can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 like, that is between any two lines it is 20 meters. So, 20 into 10. So, our head will be, gross head will be 200 meters, 200 meters, right. So, these are the first part questions. So, you can see now the idea is, after doing this course you should be able to identify a location and the project components and see whether they are plausible. That is, if you have a say a housing scheme, you can't do it. If there are water schemes, then you have to look at. Then your catchment you can see in the upstream. I will not try to confuse you with marking catchment, because you have to do a lot of work and understand, but for the time being be satisfied with this. If you can do these things, then it is better. So, we could have come on the left bank also here like this, and somewhere here and gone down. That is also a possibility. That is also a possibility, but choice depends upon availability of roads, availability of land, easiness of transportation, right. So, depending upon those things, we will select which bank to construct our canal, penstock and powerhouse, right, canal, penstock and powerhouse. I hope this part is clear to you. So, going to the second part, you can see part B. Assuming the given flow data table is applicable to the diversion point of your plant, prepare the flow duration curve for the location. So, for that they are given a data set. So, the best thing is to copy this entire thing, data set, onto Excel sheet. Okay, now we have got the Excel sheet converted to the PDF sheet converted to Excel. We can see the data points here. So, we can see October, November, December, January up to September here. Each day, day 1 to day 31st, flow rate on October 1st 3.354, October 2nd 2.5, June 3rd 0.607, and so on, right, and so on. So, so now we have to work on it and then see what are the, let us see what are the questions that were there raised in the tutorial, right. Assuming the given flow data is, prepare the flow duration curve for the location. Now, we have to study this data set, right, study this data set. So, we can see. So, one of the better ways of studying and seeing what is the range of values that we have here, and what are the ranges. So, let us see what is the maximum value here. So, I will give the entire data range and see what is the maximum value in this data set. It is good to know, then you can, when you categorize them, that is easier then, right. Okay, the maximum value is 9 point, is the maximum value, right, is 9.335. Let us see what the minimum value. So, the minimum value is 0.602, 602. So, I think so we have to deal with data points between these two, right, these two values. So, up to 9.355, let us set up to 10, right. So, let us now the smallest size is 0.6. So, let us make class intervals in the range of say in steps of 0.5 up to 10. So, we will open a new sheet. So, I will write the class intervals like previously, right. So, 0, next is 0 plus 0.5, right. Oh, I type in the wrong way. I selected the step by 0.5. I think my numbers are small. How can I zoom this? Umesh, can you zoom it a little bit so that participants can see it clearly? View. Okay, here. Okay, right. So, I selected, you can select any point, does not matter. So, 0 class interval I have selected as 0.5, right. So, I will copy and go up to about 10. One more. Okay. So, this 0 means this 0.5 means really 0.02, 0.05, right, that is the class interval, but I have just typed it as 0.5, right. This is really 0.5 to 1.0. So, we must count the data points in this range and put the number here, frequency here, frequency of occurrence, right here. So, from this table, for example, 0.5 to, so we can see there are many points, 0.6 comes there, 0.5 to 1, there are many data points. So, we can't manually do it, that is why we are going to use the frequency command. Therefore, we can ask the frequency command to count and put into these class intervals, right, put into these class intervals. How do you do that? You select this cells that you want the counted numbers to appear, and we will put a one cage more, one data point more, because in case there are larger numbers than 10, all of them will be counted and inserted into this additional cell, right, inserted into the additional cell. So, I selected this and now I start typing the frequency command plus frequency, open brackets, then it gives the hint here, data array, bins array, right. Data array is our data table. So, I will give the entire data table, not the date numbers, but the data points here, right, comma, and then the class interval array. Class interval array is this one, not the column A, right, then there will be a syntax error. So, I will give this column. Close brackets, right. Then you have to type those three keys, control shift enter, that is the frequency commands executing command, right. Control shift and enter. Now, you can see all the counted numbers are inserted into the selected cells. This last number is 0 because our maximum data point was 9.3 something. So, there were no point above 10, therefore, it is there is nothing to be put here, but if there were any could have been here, right. So, there are large number of data points between 0.5 to 1, right, and then this is really 1.0 to 1.5, right. There are 40 points, 40 data points during the year, right, during the year. So, now we can convert this to a flow duration curve by the technique I told you earlier, right. So, you can get the probability. So, altogether there are 365 data points. So, we can count it, the total is 365 data points. So, probability of each day's flow is really the frequency divided by 365. Right. I will put it to, I will adjust the decimal points to 3. So, this is the probability. Then we can calculate 1 minus p to get the inverse shape. You can do parallelly, right, you can do parallel with me. And then to get the percentage you can multiply by 100. I do not do it in one step because then that will be confusing to some of the attendants. Again I will adjust the decimal point say to 1. Here I made a mistake there because we have to get a cumulative frequency first, right. So, I will insert a column here. And then calculate the probability. We have to first calculate the cumulative frequency. And then calculate the probability. So, I made a mistake there. Okay. And now calculate 1 minus p. T5. Okay. Now the rest is correct. Now we have the Q flow rate and the exceedance or the percentage time that flow rate is available, right. So, we can now draw a graph between this column and this column, right, a graph between these two columns, which will be your flow duration curve. So, let us do it and see. I will select I am a bit unfamiliar with this version of Excel. I selected the maybe my selected chart type was not correct. Let us see this one, it will work. Select data, add x values will be your exceedance. And y values will be the flow rates. Flow rate here. Now, you get the flow duration curve. You can give a title, etc. Oh, did I do something wrong? I think I did some mistake. Y values, flow data. Okay. 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 Now, you can see you get the flow duration curve. You can do it nicely in a better shape, better I think the line is too thick and all that, but this is how you get the flow duration curve, right, flow duration curve, and then you can get the charts, grid and all these things, then you can easily get the numbers, etc. right. Anyway, I will not waste time on that. You can see, right. So, this will be your flow duration curve, right, flow duration curve. Now, you are asked to get let us go back to our, I hope any questions up to this, right, any questions up to this from the online or the physical attendance here, right. So, here you can see now for given flow how many percentage of the days, right. For example, I think we should get this the grid lines and all that, format this, so that you can Anyway, anybody having problems in getting the flow duration curve? Any online participants, you should be able to do it. And then let us go to, once you go there, you can get the flow corresponding 12% exceedance as the rated flow. So, you can go to your this thing, developed curve and mark 12%, find out where the 12% and get the corresponding flow rate. Let us see it is, you can get the exact value, right, but let us assume that this is 9.8. 14. So, it is somewhere around, I will guess around 1.8. You can get the exact value by enlarging this and having the grid lines. So, it is about 1.8 cubic meters per second, right. You can get the exact value and tell me if you want. It is about 1.8 cubic meters per second, right. So, you can get the exact value. Determine the type of turbine and its capacity. Assume single turbine power plant. So, you can see now your head is, we found 200 meters, right. In my particular case, we found that it is 200 meters approximately. Head is 200 meters and the flow is 1.8 cubic meters per second. Now, you can go to a turbine selection chart. I can refer to my notes, or you can otherwise try the net. Let us try the net. Let us search and see. Here you get many kinds of turbine selection charts here. For example, this one, right. So, most of them are the same. So, they will give the same similar advice, different suppliers will have. So, this is having a lot more details, many turbine types are here. Earlier we restricted our discussion to Kaplan, Crossflow, Francis and Pelton and Turbo turbines only, but here they are talking about many other versions that are available, right. There are various other versions. So, we can go use that too. We can go to a simpler one if you want. Now, you can see, now you can mark your flow rate 1.2, sorry 2 is here. So, 1.8 is somewhere here, I think. Oh. Here, right, this is 2. So, 1.8 is somewhere here, you can mark 1.8 and the head is 200. So, 100, 200 is somewhere here, right. So, you are almost close to Pelton. So, you can go for a Pelton turbine, right, Pelton turbine. So, the some of these charts will have some limitations, because they are made for small hydros. So, if you go outside, then you have to go for some other chart and see, right. So, you can go for a Pelton turbine in this case, you are almost close to there, right, or else you do not have multiple options as per this chart. You can see some other chart and see whether and also we have to be careful that you refer to an accurate chart, right. So, better to go for to a good manufacturer site and obtain a similar chart, right. There are good turbine manufacturers. For example, there are German here for example. So, we once bought equipment from this supplier. He is a good supplier. So, he will have lot of information in his these various sheets. So, there are many such equipment manufacturers you can refer to. You can search for small hydropower turbine manufacturers, and among other things they will have somewhere in their documentation turbine selection charts. I do not know exactly what is the place. Let us go to turbines and see. Here you can see this is a good turbine selection chart. So, all the manufacturers will have similar charts, right. Here you can see. Now, our flow was 1.8, 1.8 and 200 here, somewhere here, right. So, you can here as per this you can go for Tergo, Francis or Pelton, or multiple types are possible. So, this is a dependable one because this is given by a manufacturer through his own experiment, but in some other graphs you are getting in the internet may not be that accurate. That is why I came here rather than using the one that we looked at, because their source we do not know, but a good reliable manufacturer will give a good turbine selection chart. Now, here he says large turbines on request. So, having large flows, right, and bigger heads, your size will be much bigger, right, and smaller turbines also on request. So, this is generally what are used in above 100 kilowatt, you can see above 100 kilowatt and below 35 megawatt, that is the range he is just given us, right. So, our power project is 1.8 200 somewhere here, right, somewhere here, which I can plot here. I can't draw because this is an internet page, okay, right. So, this is how you do select machines, right, design a project, right. Then we are asked to estimate the annual electricity generation, right. We have done the determine the type of turbine and capacity. Capacity now you can calculate, right. You can calculate using P equals efficiency into Q rho G H. The capacity we calculate for maximum efficiency, assume maximum efficiency as 90%, right, for the turbine, and the other equipment suitably, generator about 96%. Let me write here. So, we are asked to calculate our head is 200 meters, flow is 1.8, you can get the exact value, I just estimate like that, cubic meters per second, right. And then our equation is efficiency into Q rho G H. Efficiency we have to get, right. So, the efficiency will be efficiency of the turbine efficiency of the generator, efficiency of the transformer. Let us stop there, otherwise you can put the transmission line, etc. This is gross head 200. So, net head we can say net head is about, we will allow about 3% loss in the penstock. So, it is about so we will deduct about 3%, net head is about 194 meters. So, turbine efficiency we will take say maximum efficiency is 0.9, generator 0.96, transformer 0.98, right. Someone can simplify these things and tell me how much is this 0.9 into 96 into 98. Then efficiency Q is 1.8 Okay, we will have to, we assume that we have already deducted the environmental flow. Rho is 1000 10 to the power 3, G is 9.81 into H is 194. What is this efficiency value? 84. This say someone says 0.84, and then the plant capacity by multiplying this all the things. You can forget about this, this is in watts. So, you can make it kilowatt by removing this 10 to the power 3. So, it will be kilowatt then. How many kilowatts of our plant's capacity? 2900. So, our plant as per this calculation has a capacity of 2900 kilowatt, 2.9 megawatt for the location that we have selected, right. So, depending upon this point you have selected, it will be different, your head will be different, etcetera, right. But we have assumed the data table applied to you, but in reality you have to get the real data table worked out by a hydrologist, right, hydrologist. Now, it further asks, estimate the annual electricity generation. Then we have to expand this, I will relocate this to elsewhere. Here now we can up to here we use for flow duration curve derivation. Now, we can go for our power calculation, right. So, let us assume some values, right. Let us assume this generator and transformer efficiency to be 0.96 into 0.98, how much? Can you work out? 0.96 into 0.98, that is the transformer efficiency into generator. We will assume that to be constant, but the turbine efficiency we can't. Efficiency generator plus transformer, how much? How much is it? 0.98 into 0.96, 0.94. 0.94. We will keep it because we might need that, right. And so, and the Q. Now I want to introduce something new here for you. Last time I did not complicate it for you. Now, we see here, right, I took Q as 0.5, right, 0.5, and let us take a minimum flow, Q minimum, that is the environmental flow. Let us say environmental department said it to be 0.3 or 2, whatever, right. Okay. And now, now here, now in the previous discussion I asked you to take 0.5 as the Q and deduct 0.3 from the, can everybody listen? Everybody, right. Here in the last calculation we took here the available Q as Q available for power generation, right. We took it as Q minus 0.03, right, Q minus environmental flow. Can you remember Q minus? But here now we can make it more accurate by looking at this. This data point, say 271 data points, I will put a color here, right. This 271 data points are points between 0.5 and 1, right. It is not always 1, it is the data points can be in between that, right. So, rather than assuming flow to be 1, for 271 days, we can say it is the average of these two, that is better way, right. Average of these two is the flow available on these 271 days. So, I can make my calculation more accurate if I write here flow minus environmental flow, right. I can write it like this, plus open bracket, right, 0.5 is the previous data point for previous q value, plus present value, open, divided by 2, then minus environmental flow, right. So, this will be more representative rather than saying 1 minus 0.03. Then we assume always 271 days to have 271 days to have flow equal to 1, which is introducing an error, which can introduce. So, this is a better estimation. So, we will go on doing this. Okay, right, Q available. Now, we have selected 0.8 as the 0.8 for the 1.8 as our rated flow. Therefore, we can lock it there. From this point onward, we can say flow available for power generation is 1.8, because we can't generate more than that, right. We can generate more than that. So, I will after 1.72 I will lock it to 1.8. Because even though the river has water, we can't use our machines, all the components are sized to, right, all are sized to handle water rate of 1.8 cubic meters per second, right. Now, I have to get, right, we have to get efficiency of the turbine here, efficiency of the turbine here, right. So, therefore, that we will have to again rely upon a efficiency curve of Pelton turbine. So, we have selected Pelton turbine. So, we can refer to a Pelton turbine. Let us see such a graph is available with in the net. I went to, you can see that there are some graphs here. So, you can get from a reputed manufacturer. I will take a typical one and use, but you can see you can this is the flow rate as proportion of design flow, but this is a percentage flow, right, this is a percentage flow, and for the Pelton it has, as we all know, quite flat, right. So, this is given as a percentage. So, we have to know our percentage flows here, right, percentage flows here, that is out of 1.8, what is the percentage here, right. So, we will have to, we will insert a column again here. divided by 1.8. Okay. So, you can now approximately get from that curve, right, corresponding to various points that we are into 0.1 to 0.4 etcetera. Of course, you must do it in accurate way, right, 0.1 to 0.4. So, let us say 0.4, you can see the Felton has already by 0.4, it is already 90 level. So, you can see it is no problem assuming all the values as 90 for our case, right, already it is in 90, right. So, in this particular case as per this particular example and also as that graph, almost everything rise there. Turbine efficiency also appears to be constant, right, because our low flows are less, but it is not the case always. Remember, if you selected Francis turbine, you can see it is different. You must have at least 0.2 or 20% flow to start the operation, right. So, below values you have to remove, and then part load you can see 0.4, efficiency is something like 60%, right, efficiency is 60%. Therefore, you have to put, if you selected Francis turbine at 0.4 percentage per flow is 0.4, this will be 60%, right, 0.6. Accordingly, you have to give the efficiency values, right. Efficiency. Now, you can calculate, right, P turbine at turbine shaft, what is the power available, that is our equation, right. Efficiency into efficiency will be now generator and transformer has 0.94 into turbine efficiency is this cell into, that is efficiency, Q is this value, Q, rho we will 1000 we will take out and say this is in kilowatt, G 9.81, H is 194 net head in our case. Sorry, 194. Why have typed here something wrong? See whether any typing mistakes, that is right. It is 0 because flow is 0, we will copy it all down up to here. So, it says 2898, our calculation earlier said 2900. So, we can round it over to 2900 if you want. Okay, so, this is the turbine. It is not really the turbine, it is really the P output, because we have already included efficiency of the generator and the transformer. It is the power output of the at the terminals of the transformer, right. And then we can calculate energy for each day, that is power into power is, this is in kilowatt, right, this is in kilowatt, because we have taken that 1000 term away, rho has 1000, we removed it, and therefore, we say it is in kilowatts, right. Therefore, energy will be P kilowatt into 24 hours, right, 24 hours. into 24 kilowatt hours into number of such days. Number of such days are the frequency, right. First one is 0 because there are no such data points, but other days there will be. So, this is coming in kilowatt hours. Okay. So, every day we know how many kilowatt hours have been generated as per this calculation, right. Then we can see the total, right. You can put it in megawatt hours if you want, if the large numbers are large, right. So, this is in kilowatt hours. So, then we can sum it up, say annual energy. See, now it is a large number, therefore, I will divide it by 10 to the power 6, last cell value I will divide by 10 to the power 6 to make it gigawatt hours. You can see 13.12 million units of electricity. Right. So, our project can produce 13.13 gigawatt hours, right, gigawatt hours. I just divided this by 10 to the power 6, otherwise the number is too big, right. So, 13.13 gigawatt hours. So, 13.13 million units. So, if you are selling each unit at 10 rupees a unit, so every year you get 131 million rupees as income, right. So, you can use this number now for your cash flow calculation, and the project cost you have to estimate, then you can do a cost benefit analysis, right. Any questions? I think these are straightforward for engineers. So, I am just doing it for you just to understand, right. You can do much faster than me, we are much quicker in the keyboard and all that, not like me, right. And you can do it in smarter ways also, right, smarter ways, right. That is, we can even use MATLAB codes and all these things without doing all this the way conventional way, but you must understand the reality, how it is done. Then actual implementation you can use a modern tool and do it, right. I hope that you will do not get confused with this kilowatt hours, and that I took away the 1000 from that equation. I am assuming that all these things are straightforward for your level of right competencies.
Sir, I have a doubt while taking the efficiency of the turbine. So you had said when we are going for Francis, is it all the same 0.9 or there a change in the efficiency that column?
Yeah, that I agree with you. It need not to be the same, but you know that as per this particular chart that I referred to, when you get the percentage, this is the horizontal axis, see flow rate as proportion of the design flow rate. Our design flow rate is 1.8. So, I calculated the column here, that percentage flow column, that is flow, available flow divided by 1.8. Here cell is H5 divided by 1.8. So, here you can see our flow is 0, 0.12, 0.4, 0.68 and so on. but as per this particular chart, right, when it comes to 0.4, efficiency is already, when it comes to 0.4, efficiency is already 0.9. See, flat, we are already in the flat region, right. That is why I put 0.9 as the efficiency, because we have selected the Pelton turbine. But if we had selected the Francis turbine, which is also possible as per the that turbine selection chart, in that case what you say is very correct. When it is 0.4, then efficiency is 0.6 only. Therefore, we should have here at 0.4, here this number should be 0.6 then, if we selected Francis turbine, and 0.68, at 0.68 we can see 0.68, 0.7 is here, 0.68 is somewhere here. In that case, Francis is having something like 85 or 86, right. So, you have to put the correct value here, right, at 0.68 percentage flow, it should be 0.86 or so. So, actual values you have to put, right. So, but here since the Pelton is already in the 0.9 region, that is why I put all these values 0.9. I was not very careful about these things, because there are no data points there, because the frequency is 0, right. So, there are no days when the flow is this small. So, we do not have to worry about that, we can start from 0.4, right. So, but as per this at 0.4, already the Pelton has 0.9, that is why I put 0.9, right. But here it is a little bit going down, therefore, if you want you can incorporate that also here at the last values here, maybe 0.88 or something, right. So, of course, you can make it more accurate by doing these things. Hope I answered your question.
Okay, sir, but while designing and purchasing, which one will prefer then, Francis or Pelton?
That depend upon your prices, choices, etc. Now, you must see how much they are quoting for the Francis unit and the Pelton units. And now, the Francis will have a little lower efficiency, no. Therefore, the total energy generation might be also, you can see there are 200 data point, 200 days, the percentage flow is 0.4, right. And if the efficiency is 0.6 during those large number of days, your energy project production will be hugely affected. Now, let us put it and see. I put it here this Francis turbine values, right, 0.5, 0.55 and 0.4, 0.6, right, at 7, at 7.7 it is about 84. I am putting approximate value, you can put the 0. We can get the exact values and put them here, and then let us assume the balance is correct, right, 0.9 and so on. Now, let us look at the total energy generation. It has gone down to 10.5 from 13.13, right, substantial decrease in the annual energy production, right. So, if you go for Francis, your annual energy generation will be low, and therefore, your income will be low, annual income. But if the total package price of the package manufacturer gives you for the Francis is considerably lower than Pelton, then you can still consider. That all depends upon your cash flow calculation, economic evaluation. So, you must do one cash flow evaluation with Pelton turbine and another cash flow analysis with Francis turbine, and maybe Turgo was also possible. Another cash flow analysis is Turgo. You must get offers for all three from the manufacturer, right, and then with certain assumptions you can get the civil costs also approximately done, and then total project cost, then do the economic calculation, but your annual energy generation for the three types will be different. Now, you can see this is 10.5, previously Pelton had 13.1, right. So, your annual income is going to be different and project cost will be different, because they will charge differently for the two turbine types. I hope I make sense to you. Did you get my point?
Thank you so much.
Okay, thank you. That is a good question. Okay. So, now we have converted it to Francis turbine, that is why these efficiency values are different now, right. Okay. Turbo turbine is not here, right, but you can look for a, if you are interested, you can look for a chart having turbo as well. There are charts, there are plenty of these things available here as well as with the manufacturers. Here you can see, let us see what this manufacturer says, turbo turbines. If you can remember the photos we looked at, can you be familiar here? Now, I find that this manufacturer in his website has put our plant. This is our Velihulliya plant, photo of Velihulliya plant, if you can remember, right. He has opted for that. I judge it from these windows, right, which we did. Yeah, okay. Any other questions anybody is having? I am just wondering here. Okay. I did not insert more complicated questions here. Now, if you go for 2 turbine option, right, 2 turbine option, then you can modify this table. You can logically think and modify this table and accordingly see how much will be the energy generation, right, if you have 2 turbines. And when you are opting for 2 turbines, turbine operation will also be different, right. Turbine operation will also be different. Let me explain it a little bit. I will take a blank slide then explain. Here, now you can see, now we have set the plant and plant is in operation, and we have 2 turbines, 1 megawatt into 2, right. Yeah, got to get it to presentation mode. Okay. And now you have 2 turbines, 1 megawatt into 2 turbines. Now, suppose you start to, now it is dry season and so you get the rains, and you start the plant, right. You start the plant, this is plant output megawatt or kilowatt, right. So, when you get when you have water, this is time. So, you start the first unit and load it. Up to 1 megawatt you can load 1000 kilowatt, right, 1000 kilowatt. Now, you find there are still more water available, right. Now, you have more water, right. Then you can, what can do? You can start the second unit, right. You can start the second unit also, because first unit is now full load and second unit can be started, right. Second unit can be started. Now, how do you do that? Now, you keep this on 1000 kilowatt, the full 1 megawatt, and start the second one from 0. That is not the way. Then the second machine will run on very small flows, right. what we will do is we will reduce this a little, we will reduce it to 75%, right, and then start the second machine, right. So, your total will be then increasing, right, because we reduce this one in order to start the second machine with a larger flow rather than starting with a small flow, right. And if there are still more water, we will take the second machine also, first machine also to the full load, right. If there is still more, this is maybe this is this, let us assume this is as 800. So, this may be 1800, and then you start the second machine also, first machine also to another 200 to make it 2000, right. So, likewise in operation, depending upon the type of turbines you have to optimize how it load and unload it. Now, when the water level goes down, right, how do you stop machines? How do you keep the machines in the best operation point? That depends upon the efficiency curve. So, we will try to keep together the machines in the better efficiency point in operation of the power plant. So, all these things will enhance the total power generation. So, accordingly you have to think about this when you have multiple turbines, how your plant generate electricity. Therefore, you can further increase the total by, right, optimally operating the two turbines and accordingly reflecting that in this Excel sheet, right, accordingly reflecting it in the Excel sheet, rather than saying one turbine until it is full loaded we take it, and then the rest of the water from beginning we load on to the other one. That is not the actual way of doing it. Otherwise, you will have a smaller estimation here. So, those I think fine points you have to do it with experience, and also you can logically argue, you all are engineers. So, you should be able to logically argue and arrive at various refinements to this calculation, right, various refinements to this calculation. And also now we assume the transformer efficiency and generator efficiency to be flat from no load to full load. So, you can think about that, if there is a substantial difference, you can incorporate those curves also into this rather than getting them as constant, and thereby making your calculation more accurate, right, making the calculation more. Now, here we assume only the turbine efficiency is changing from full load to no load, right, but for transformers and for generators also there will be a variation, right. So, if you want, you can accommodate that also, you can look for a generator efficiency curve, right. You can see whether anything is available. Not the capability curve, I want to capability curve is that Q1. I do not know whether this is the generator, I assume. Here, can see. So, they are changing as per this chart, I do not know whether they are 100% right, and frequency versus load kilowatt and whatever. You can see they are not ranging from very low values, but can range from these are for different power factors. Blue one is the 0.8 power factor, let us assume that one is the applicable. You can see it is ranging from 0.83 I think these are two small values. These 2 9 generators are more efficient these days. This curve cannot be true. They are in the 90, 95, 96 range, right. There are no 10% losses. Here this may be correct. So, these are in 97, 98 in that region, right. This is a wind plant efficiency now. That is why you know that using these efficiency curves from the net is quite dangerous sometimes. Let us look for a generator manufacturer. Hitzinger is good manufacturer. Alternator Hitzinger, that is a good manufacturer. We bought our projects from this manufacturer. You can see for the first choice for small high power plants, small hydros. I just looked at their brochure, but I do not know whether it has any efficiency curves. Here are some numbers which I cannot read, right, but sometimes good manufacturers indicate their efficiencies, right. So, you can get the generator efficiencies and incorporate them into our Excel sheet if you are really want to make it more accurate, right, more accurate, and for the transformers also. Any other questions? Otherwise, we can wind up. So, I have given you some insight by you doing some hands on work. So, that just by listening to me you will not acquire knowledge. So, you must do it yourself. So, this is an example. Now, you have the capability of identifying a site by looking at a contour map and then deciding a project, doing an approximate calculation, and from office even you can approximately calculate and tell and discuss a project opportunity, right. Of course, you have to visit the site as we saw in the pictures there yesterday during our virtual field visit, that you have to go to the ground, right. You can't do everything from office. Hydropower is in the jungles, right. So, you have to go there and erect the projects, right, construct projects, and also these all the measurements, estimations we have to get validated and confirmed by site visit, site measurements, surveys, etc. Right. Okay. If there are no any other questions, we will wind up our tutorial session here.
Sir?
Yes, please. Yes.
Sir, I have one question regarding yesterday's virtual power plant. Is it okay? Can I ask now?
Regarding
yesterday's virtual power plant visit.
Okay. Yeah, you can ask.
Sir, like regarding the controllers, yesterday when we were showing the controller, there was a water controller thing which was given to the powerhouse. So, other than that, like for the voltage and frequency regulation, maybe if it is is it grid connected or islanded mode? Yesterday's power plant, I didn't understand. I missed that point.
No. I just spoke about the water level controller because it is important for the from hydropower engineer's point of view, keeping the water level constant in the forebay tank. There are many controllers in the control system of the power plant. There are automatic voltage AVR and various other governors, and also various other controllers in the normal power plant. So, we did not go into electrical engineers details. So, all these controls will be there in a hydropower plant. So, we did not go to those details. We went to the design of a small hydropower project from a hydropower engineer's point of view. He will buy the entire package from a supplier, and install there.
Okay.
It will include all this
Okay.
there will be a nowadays all are PLC control. This machine is starting, stopping, all will be PLC controlled, right, no human intervention, and so all these controllers will be there.
Uh, Thank you, sir. Thank you
Okay.
so much.
Okay.
So one more question regarding the maintenance, especially compared to other power plants, the maintenance of hydropower plant is very crucial.
Yeah.
So how do we look into that aspect,
Yeah, you know,
especially for a small hydro?
yeah, small hydros, you know, these turbines and the generators are very reliable. Therefore, they will have very less maintenance, very less maintenance. But of course, there are maintenance in the civil side. You will have to regularly clean and clear the canals, forebay tanks, etc., and look after your penstock without any corrosions and other things on one hand. But other than that, in a hydropower plant, minimum maintenance. But if you have inserted the gearbox between the generator and the turbine, gearbox has certain amount of annual maintenance, because gearboxes are, you know, not easy to maintain. You have to change oil sometimes as per the manufacturer's recommendations, and also attend to various other functionalities like replacements time to time, maybe not annually, maybe during certain periods. Gearboxes have more maintenance compared to other components. Other than that, I do not see much of maintenance in hydropower plants, other than if you have a good system, if you have installed good lightning arresters, surge arresters, good earthing system without getting damaged during lightning, in that case you will have less maintenance. But I have seen some plants getting you know, problems due to lightning, and even generators getting burnt. When a generator is burnt, you know, repairing is not easy. If you can't do it in your home country, you will have to send it back to the manufacturer, right. So, you will lose several months of generation, several months of generation. So, these are also considerations for putting multiple machines. When you have two machines, if one generator is damaged by lightning, you have at least have other machine to run, right. So, you have some generation. So, these are also, but of course, when you have double machines, you have excess cost, because double you need space in the powerhouse, you need two control systems, etc. But other than that, there are advantages also. So, maintenance in a hydropower plant is minimum, and compared to any other power plant, I would say. Even in a solar power plant, you have lot of maintenance, you have to wash the panels, right, you have to wash the panels, etc. It may be routinely every week, otherwise your generation goes down, and so on. But in a hydropower plant, you do not have such kind of things, but you have to maintain the equipment. For example, now you refer to the water level controller. Sometimes, because water level sensor is at the top part, forebay tank is in a hill, top part of a hill. So, they are liable to be attacked by lightning. So, I have seen some power plants where the sensors are damaged and they could not find replacement easily. Then there is no water level control. So, there is a man in the forebay tank keeping a walkie talkie. When the water level goes up in the forebay tank, he gives a call to the powerhouse, increase the generation. Therefore, somebody will press the buttons, right, press the buttons to open up the needle valve, right. You can manually do, manual options are always there, and then the water level comes down. When water level goes down, he gives another call by walkie talkie. So, you know that very difficult to maintain. So, 24 hours they have to do it if the water level control is not working. I hope I answered your question.
Yes, sir. Thank you so much. It was a very insightful session
Okay.
with good practical informations a lot. Thank you so much.
Okay, thank you. Thank you. Yeah, tell me.
Can we estimate, predict the power generation based on the available source of water, sir?
Yeah, I think that is what we have done here. Now, depending upon the available water here in this column, we have predicted the amount of power we can generate, right. So, this water availability has been predicted by the hydrologist. He has said here, for example, there are 271 days with the flow in between 0.5 to 1.0 cubic meters per second, in that range. So, this is the prediction by the hydrologist based on 30 years historical data, right, 30 years historical data. So, we our power generation we have predicted accordingly, power generation and the energy generation we have predicted accordingly. Now, incidentally you can see this 271 days our power generation is only 772 kilowatt, whereas our plant has a capacity of nearly 3 megawatt. So, it is running mostly on part load. That is why it might be advantageous to put two machines. When the plant will be, then each machine will be running at maybe 90% efficiency, right. So, the two machine option might be better for this particular flow regime. I hope I answered your question.
So can we implement the two basin concept here, sir?
Yeah, that can be done, yes, that can be done, but I do not have time to go that is a bigger calculation. So, I think you yourself can do it, put one machine and start the second machine after it, right. Maybe you can put 1000, if it is a Pelton turbine you can put equal turbine 1500 into 2, assume this 2898 is 3000 and put 1500 into 2 and take the first machine and go to the maximum power, right, 1500, and then start the second machine, right, start the second machine. Here you have to restrict it to 1500, right, and then take the other machine from here point onward. Then your efficiency values will have to be again repeated. This will have to come again here, the second machine is starting there. Here, right, and then first machine ends here and second machine starts here, that is 1500 plus this point, right. So, your flow will be now not 1.72, it will be again starting from 0 or corresponding to the next step, right. So, this will be starting again from 0 for the first machine, right, and then again going ahead. So, you have to accordingly adjust your columns. So, second machine will be starting here and going, and then once the second machine also 1500, both machines will be in operation, right. That is how you do it. Then there are 3 machines, accordingly you have to adjust. I hope you can do that part alone, right. Okay, any other questions? So, otherwise we can wind up here, we are nearing our session.
So can you share your mail ID, sir?
You mean my mail ID?
Yeah.
Okay, I can share. I will type here.
Thank you, sir.
Yeah. Simple. anuradw@uom.lk. You can say, you are free, you can ask any question. If possible, I will answer if I know. This is my email number. If anybody wants to have an additional question, you might ask me. So, if you are in private companies, suggest to your or boss, your chiefs, if there are hydropower opportunities, why not we do it if in your area, if there are hydropower opportunities. In India, as I said in the first lecture, as per the Ministry of Energy, there are 21,000 identified 21,000 gigawatts of identified hydropower opportunities, and about 25%, that is about 4,500 something like that, have been developed. So, there are large number of opportunities available in this country which I think you should do, right, because there are environmental targets, net zero targets coming up, right. So, all these opportunities while doing solar, wind, everything, hydropower also, the balance 75% must be developed, right. So, it will be good for the country and good for the planet also, if we go for more renewable, and hydropower is one of the best renewables, because intermittency is very minimum, right. Whereas, wind and solar, you have intermittency, seasonality, diurnality. Solar is diurnal, only say 8-10 hours of input every day, generation every day. Wind is seasonal. If you take 12 months, wind may be available 6-8 months. Balance 4 to 5 months, you have zero wind or very low wind. Therefore, you have to have some other power plants for the to supplement. Whereas, hydropower is seasonal, of course, there are dry seasons, wet seasons, but other than that, steady power generation. Okay, thank you very much, and so we end our discussion here today, right. Okay, thank you.